We propose a planning framework for quasi-static manipulation tasks via an intrinsic haptic metric. Robotic manipulation requires both motion planning and physical contact with objects, but traditional motion planning always avoids contact. For example, insert a book into a crowded shelf. A traditional planner would fail to place the book into the crowded shelf due to limited space. A strategic insertion policy is needed. First, push neighboring books aside to create space. The person then applies a forward force to slide the book into the shelf. Here is our contribution. Our paper leverages on a recent framework to quasi-static manipulation. We define configuration space. C is internal state and U is control of the robot. Given a potential function, we can define the implicit manifold and other necessary components of our framework, such as haptic metric and haptic distance. Since the object state C is implicit, we apply first-order approximation on the equilibrium manifold to move U, shown as blue arrow. We utilize Newton's method to find equilibrium, shown as the red arrow. ODE can also be terminated by haptic obstacle. We apply superellipses to represent blocks. We utilize proxy to capture contact points. We use springs to represent other energies in the system. In the end, we get the manipulation potential. We combine DMP with our adaptive ODE, which computes control policy U, object state Z, and cost simultaneously. We use BBL to optimize the parameter of control policy. We first conduct a pre-calibration to determine resistive stiffness on the shelf by exerting a constant force or torque. Here are the BBL results. The initial parameters produce a straight line policy, causing it to get stuck in front of the books. With each iteration, the policy steadily improves. Our optimal policy minimizes contact force and torque. We implement optimal policy in the real world. The contact force and torque trends are similar between simulation and real-world results. To test our framework's robustness, we vary the book's initial position. Each run finds a wedging-in policy and succeeds. We also vary the shelf's resistive stiffness by making one side a rigid edge. Our framework discovers pushing the opposite side and succeeds.